In the realm of physics, the spring mass oscillator stands as a fundamental system, captivating our attention with its rhythmic oscillations. This elegant experiment, a cornerstone of Class 12 physics practicals, offers a gateway to understanding the principles of simple harmonic motion, or SHM. Imagine a weight bobbing gently on a spring, its motion a mesmerizing dance of stretching and compressing. This experiment allows us to unravel the secrets behind this dance, revealing the underlying physics that governs it. Join us as we embark on a journey into the world of springs and masses, exploring the intricacies of their oscillatory motion. We will delve into the experimental setup, step-by-step procedures, and the art of observation. Together, we will unlock the mysteries of SHM and discover its profound implications in our everyday lives. Before we set our experiment in motion, let's gather the necessary tools. Our stage comprises a few simple yet crucial components. A sturdy stand, which provides a firm anchor for our experiment, ensuring stability throughout. A helical spring, this coiled wonder is the heart of our setup, its elasticity driving the oscillations. A set of weights, these masses, when attached to the spring, will experience the rhythmic dance of SHM. A stopwatch, time is of the essence in capturing the oscillations, and this trusty tool will be our timekeeper. A meter scale, precision is key, and this scale allows us to measure the spring's elongation with accuracy. With our apparatus assembled, we are now ready to delve into the heart of the experiment and bring our spring mass system to life. Now that our stage is set, let's begin the performance. This experiment will help us understand the fundamental principles of simple harmonic motion, SHM, and the behavior of oscillatory systems. Suspend the spring. Gently hang the helical spring from the sturdy stand, ensuring it hangs freely without obstruction. This step is crucial, as it sets the foundation for accurate measurements. Establish equilibrium. Attach a weight to the spring and let it come to rest. This is our equilibrium position, the starting point of our oscillatory journey. The equilibrium position is where the forces are balanced, and the spring is neither stretched nor compressed. Measure the elongation. Using the meter scale, carefully measure the distance the spring has stretched from its original, unstretched length. This elongation is a key variable in our experiment. Accurate measurement here ensures the reliability of our results. Displace and release. Gently pull the weight downwards a small distance, then release it. Observe as the mass begins to oscillate up and down, marking the start of SHM. The motion you see is a perfect example of how energy is transferred between kinetic and potential forms. Time the oscillations. Using the stopwatch, measure the time taken for the mass to complete 10 oscillations. Dividing this time by 10 gives us the period of oscillation, a crucial parameter in understanding SHM. The period is the time it takes for one complete cycle of motion. By carefully following these steps, we can precisely measure the spring's elongation and the period of oscillation, providing us with the raw data to analyze the magic of SHM. This data will allow us to delve deeper into the principles governing oscillatory systems and their applications in the real world. As the mass dances on the spring, it tells a story of motion and forces. Our eyes become scientific instruments, capturing every detail, meticulously recording the nuances of its motion. Each observation is a piece of the puzzle. Here's what we need to observe and document. Initial displacement. Note down the distance you initially pulled the weight downwards from its equilibrium position. This initial measurement is crucial. This displacement dictates the amplitude of the oscillation, the extent of its swing. Time period T. As you time the oscillations, ensure accuracy by measuring across multiple cycles. Consistency is key. Remember, the period T is the time taken for one complete oscillation. Number of oscillations. While 10 oscillations are commonly used for calculation, you can experiment with different numbers. Trying different counts can provide more insights. More oscillations often lead to greater accuracy in determining the period. Damping. Over time, you might notice the oscillations gradually decrease in amplitude due to factors like air resistance. This is known as damping. Carefully observe and record this damping effect. It provides valuable information about energy loss in the system. By meticulously recording these observations, we ensure no detail is missed. We create a detailed account of the spring mass system's behavior, capturing its essence, paving the way for a deeper understanding of the underlying physics. This meticulous approach is the cornerstone of scientific discovery. Section 5. Decoding the dance, understanding simple harmonic motion. The rhythmic dance of the spring mass system isn't a random jig, it's governed by the elegant principles of simple harmonic motion, or SHM. This motion is not just a fascinating phenomenon but a fundamental concept in physics that helps us understand various natural and engineered systems. Let's break down the science behind this captivating motion. By delving into the core principles, we can appreciate the beauty and utility of SHM in our daily lives and advanced technologies. First, let's talk about the restoring force. This force is crucial as it drives the oscillatory motion, ensuring that the system returns to its equilibrium position. The key to SHM lies in the spring's nature. When a spring is deformed, it stores potential energy, which is then converted back to kinetic energy as it returns to its original shape. When stretched or compressed, it exerts a force to return to its equilibrium length. This force is proportional to the displacement, following Hooke's law. This is the restoring force, always acting in opposition to the displacement, pulling the mass back towards the center. Next, we have periodicity. This characteristic is what makes SHM so predictable and reliable. The motion is periodic, meaning it repeats itself over fixed intervals of time. This regularity is essential in many applications, from clocks to musical instruments. This period, T, is determined by the mass, M, and the spring constant, K, a measure of the spring's stiffness. Finally, there's mathematical harmony. The equations governing SHM are not just functional but also aesthetically pleasing. SHM is beautifully described by sinusoidal functions like sine or cosine. These functions provide a clear and concise way to model the motion. These functions elegantly capture the smooth back-and-forth motion of the mass. They allow us to predict the position and velocity of the oscillating object at any given time. Understanding SHM allows us to predict and analyze the behavior of countless systems beyond springs and masses, from the swinging of a pendulum to the vibrations of molecules. This knowledge is foundational in fields ranging from engineering to quantum mechanics. Section 6. Tips and tricks. Ensuring a successful experiment. Like any good performance, a successful spring mass oscillator experiment relies on a few key techniques. Smooth release. When you release the mass to begin oscillations, ensure your touch is gentle and doesn't impart any sideways motion. A clean release leads to cleaner data. Eye-level measurement. When measuring the spring's elongation, position yourself at eye level with the lower end of the spring to minimize parallax error and ensure accurate readings. Multiple trials. Don't settle for a single measurement. Repeat the experiment multiple times, varying the mass and the initial displacement to gather a richer data set and improve the reliability of your results. By incorporating these tips, you can elevate your experiment from ordinary to extraordinary, ensuring accurate and insightful results. Section 7. Avoiding pitfalls. Common mistakes and how to steer clear. Even the most seasoned performers encounter occasional hiccups. Let's anticipate and avoid some common pitfalls in this experiment. Ignoring air resistance. While we often idealize systems, neglecting air resistance can introduce errors. Minimize this by using a heavier mass or conducting the experiment in a less breezy environment. Excessive displacement. Pulling the spring too far down can lead to deviations from ideal SHM. Stick to small displacements to ensure the restoring force remains proportional to the displacement, a key characteristic of SHM. Parallax error. When measuring the elongation, ensure your line of sight is perpendicular to the scale. Viewing from an angle can lead to parallax error, skewing your measurements. By being mindful of these common mistakes, you can ensure a smoother, more accurate experiment, yielding reliable data that reflects the true beauty of SHM. Section 8. Springs in action, real-world applications. The rhythmic dance of the spring mass system isn't confined to the walls of a physics lab. It resonates throughout our everyday lives, underpinning a plethora of applications. Vehicle suspension. From cars to bicycles, springs play a crucial role in absorbing shocks from bumpy roads, ensuring a smoother ride for passengers. Clocks and watches. The precise oscillations of a spring mass system are harnessed in mechanical clocks and watches to regulate timekeeping. Musical instruments. From the strings of a guitar to the reeds of a clarinet, many musical instruments rely on the principles of SHM to produce their characteristic sounds. These examples highlight the profound impact of SHM, showcasing how a seemingly simple experiment unlocks a deeper understanding of the world around us. Section 9. Conclusion. wrapping up the oscillatory journey. Our exploration into the world of the spring mass oscillator has taken us from the fundamental principles of SHM to its far-reaching applications in our daily lives. We've delved into the intricacies of the experimental setup, mastered the art of observation, and even learned to sidestep potential pitfalls. As you continue your exploration of physics, carry with you the lessons learned from this experiment. The rhythmic dance of the spring mass system serves as a reminder that even the most complex phenomena can often be broken down into elegant, fundamental principles. Keep questioning, keep experimenting, and keep marveling at the wonders of the physical world.